Hello, my name is Magnus Egerstedt and I'm a professor at the Georgia Institute of Technology, and I will be teaching this Coursera course, Control of Mobile Robots. And this course is really going to be structured around controls on one side, which is this rather general framework for making dynamical systems do awesome things, and robotics on the other, which is a particular type of system that we're going to be focusing on. And the first module of the course is really going to be on an introduction to controls. Basically, we're going to talk about some of the key concepts that we're going to need in order to effectively control mobile robots. But what I would like to do first is talk a little bit about who I am in terms of my research interests and see how this maps onto what is actually happening in the course. So I'm a professor in electrical and computer engineering, and my research is really focusing on two rather distinct thrusts. One is an intellectual hammer, which is control theory. So this is a general framework for making dynamical systems do awesome things. And then I have this intellectual hammer that I hit on the head of an application nail, if you will. And the application nail is robotics. So I spend most of my practical time on making robots do interesting things. And that's lucky for you, because the topic of this course is exactly this marriage of control theory and robotics. And my research is really focusing on three different types of robotic problems. One I'm very interested in is swarm robotics. And the question there is, how do you make large collections of mobile robots do useful and interesting things with limited information? And we're going to see how to design swarm algorithms for mobile robots in this class. Another area that I'm interested in is behavior-based control. And the idea is, since most robotic tasks are rather complex, there is no single controller that can solve the problem, and instead you have to break the controller structure down into multiple controllers. So for instance, if you have a robot that is supposed to go to a goal, you have one controller that takes you towards the goal, but then unmodeled obstacles show up in the path or in the way. So then you have to switch to another behavior that ensures that you don't slam into obstacles. And this idea of designing multiple controllers and switching between them becomes even more important when you have complicated dynamical systems like humanoid robots and snake robots, or things that are highly articulated instead of just robots on the ground. The last area that I'm really interested in is field robotics, which really deals with how do you take these general computational algorithms that you develop in the lab and put them on robots out in the field that have to survive robustly in real conditions. And this picture here I like very much, because three of the robots that we're going to deal with in this course are actually present. So here is a little round robot. This is a Kepera mobile robot. That's a differential drive robot on the ground. We're going to control these quite a lot. Up here in the air is a quadrotor, and these robots have to be controlled in a different way, but we're going to learn how to do this as well. And right here is a little bipedal walking humanoid robot, and all of these robots will show up physically in the class throughout the various modules and lectures. So here is actually an example of what I do, and the reason why I'm showing this video is because a lot of the things we're going to learn in the class are present here. So you have, in this case, 15 mobile robots on the ground, and they have to together solve some kind of coordinated control problem. In this case, what they have to do is they have to spell GRITS, because I'm the director of the GRITS lab, which stands for the Georgia Robotics and Intelligent Systems Lab. And as you can see down on the left, there is a link to a lot of our videos that you can find on YouTube. But talking about the robots here, what they need to do is they need to use the information that's available to them and come up with control strategies based on that. And in this case, they have to figure out where they should go in these particular formations, how they should go there. They also need to deal with the fact that the robot models, the dynamics of these little guys, are surprisingly complicated, and you should not slam into each other. You should also be able to survive disturbances. So Ted here, who's a former master student in the lab, is actually messing with the system, and the controllers have to be able to overcome these disturbances and actually be robust to what's going on. So having said that, what we are going to do in the course is develop control theory, which is this general mathematical framework for making systems do useful things. And then we're going to take robotics as the main application domain, and we're going to couple robot models and robot problems to what we develop on the control theory side. And that's going to result in a number of different mobility controllers. And we're also going to discuss a plethora of different application domains found in robotics where our controllers are useful. I do want to point out, which is almost as useful, what's not in the course. This course is not a course on AI, in the sense that the robots aren't going to reason at a high level about where they should be going. Instead, someone has told the robot where it should be going, and it's our job to make it go there. It's also not going to be a course on perception, in the sense that we're going to assume that the measurements we get are already reasonably good, and they tell us roughly what it is that we are interested in and need to know. We're also not dealing very much with the actual design of robots. So a clever mechanical engineer has already built it for us, and it's our job to make this design do what it is that we want it to do. So robotics, typically, people talk about the sense, plan, act paradigm, where sensing is the perception side, the planning is the AI side, and the acting is the control side. And this course falls squarely into the act domain. And I want to end with showing a rather, I think, amusing video. This is a course that I taught on campus at Georgia Tech, where part of the course was to design controllers, very rudimentary controllers, for making these robots go to goals without actually running into obstacles. And we had students actually compete, not at the AI level or the perception level, but purely on the controls level, to achieve certain tasks. So here you see, for instance, one robot that's a little too aggressive. It's also oscillating, so there's something not perfect with this control design. It's also a little slow. The robot over on the left is more, oscillates less, but it's a little bit slower. Here we have another example of two other teams that are now competing against each other. And you will see that one robot is, again, a little over-aggressive, the one on the right. And in fact, it's going to be so aggressive that it loses track of what it is that it's doing. So this would be an example of a maybe not so successful control design. We will do this in this course. Now, I realize that I can't ship one of these robots to every one of you. So instead, we're going to do this in the studio. And we're going to together develop the control algorithms that results in, this would be the final race in this class. And take a look at Team Purple. This controller is awesome. It's very deliberate. It oscillates very little. There is very little overshoot. It's moving fast. And what's going on there is just a small and slightly more informed control design. So Team Purple won in this case. And with that, I would like to conclude this first introductory lecture to the course.